All right, last but not least, I guess we're going to look at Kepler's third law, which, remember in the last video, we got that the equation for motion in terms of r and theta was 1 over gmm squared over L squared, and then this A is a constant of integration, and then cosine theta minus theta 0. Okay, and to get Kepler's third law, we're going to compare this to a standard equation for a conic section in polar coordinates, which is a1 minus epsilon squared over 1 plus epsilon cosine. I don't know why I put parentheses there. Seems silly. Theta minus theta 0. Just real quick to see why this one's true. So here A is supposed to be the major semi-axis. And epsilon is supposed to be the eccentricity. To see this is true is actually really easy if you just think about the biggest and the smallest values of r. Well, the smallest value of r will be when cosine equals 1, and the bottom is 1 plus epsilon. So if I write it in this form, then the minimum value of r would be a times 1 minus epsilon squared over 1 plus epsilon, which is a times 1 minus epsilon. Same thing, the max value would be when this cosine is negative 1. I'd have a 1 minus epsilon squared over 1 minus epsilon. So I have a times 1 plus epsilon. And so sure enough, the major semi-axis is just the average of those two, which if I average those two, I definitely get a. So anyway, basically we're going to get Kepler's third law by comparing these two equations together. And if I wanted to turn this form into this form, well, I'd really have two equations. I'd have, if I look at those terms, I would have gm squared over L squared is, well, I need to divide the top and bottom by this a 1 minus epsilon squared. So I'd have 1 over a 1 minus epsilon squared. That would be one equation. The other equation would come from the a. So I'd have a is equal to epsilon over a 1 minus epsilon squared. So I'd have to solve both those equations, but this a was just a constant of integration. It depends on the initial speed of my object and stuff. I really don't know anything about it. It's not something physical like gravity or masses or angular momentum. I mean, you could figure out what it is, but it's not really important, especially at least for doing Kepler's third law. Okay, so there we go. That's what we get from comparing our equation for r we got last time to a standard equation for an ellipse. And let me do one more step. So another thing about our ellipse, remember that you have the eccentricity is given by square root of a squared plus b squared over a, right? Or is it minus? It's minus, sorry. That's for hyperbola. There we go. I know it has to be minus because for an ellipse it needs to be less than 1. So anyway, I have a squared epsilon squared is a squared minus b squared. And so if I'll have b squared is a squared times 1 minus epsilon squared. And the reason I want to do this is, hey, that looks very similar to what I have in the denominator there. I have just an a, right? So this would be, if I multiply the top and bottom by a, I can put a squared and a. This is a over b squared. So I'm going to rewrite this one more time. GMM squared over L squared is A over B squared, where B is now the short axis and A is the major axis. Okay. Well, how does this help me? Well, I'm going to think back to the second law real quick. We got that the change in area dt was 1/2 r cross v, which we could rewrite in terms of angular momentum as L over 2m, right? So if I wanted the period of the ellipse, well, the area of a whole ellipse is pi AB. So how long does it take to go the whole area? Well, I cover this much area in dt. So if I want the entire area, I just, distance divided by time, or area divided by dA dt. That'll give me my period. So pi AB over L over 2m. Right? So pi AB 2m over L. And now, of course, I know my Kepler's third law has t squared in it. So let's go ahead and square everything. I have t squared is 4 pi squared AB squared m squared over L squared. All right. And the only thing that I need to do now is just take this formula here and use that value of b squared. So if I get b squared by itself, b squared would be a times L squared divided by GM m squared. So this is 4 pi squared a, and then we have, a squared. Why did I square everything except the a? That's just weird. So 4 pi squared a squared, and then my b squared is a L squared over GM m squared, and then I still have the L squared in the bottom. Okay. And that's it. Just cancel stuff out. So the L's cancel, the little m's cancel, and I have t squared is 4 pi squared. A squared times a makes a cubed. Oops. I said squared and wrote cubed. 4 pi squared a cubed over GM. And this is Kepler's third law. So that was pretty easy peasy there at the end. So anyway, again, the hard step, I guess, was finding that first law. But now that we're done, let me just kind of remind you the logical progression one time. I mean, Newton had to get his law of gravitation from somewhere. So to get that, what he used was Kepler's third just for circles. I mean, this is something that was verified by experiment. And that's one thing we have to remember in physics. Physics is not just mathematical whatever. Ultimately, there has to be an experiment that everything comes from. So Kepler discovered by experiment based on Tycho Brahe's data, if something's going in a circle, then the period squared is proportional to the radius, in that case, cubed. And so from that, Newton was able to derive the law of gravitation. And from the law of gravitation, we get the three laws of Kepler, including this third law in general. So really the only thing that this rests on in terms of experiment is this Kepler's third law for circles. Once you have that, everything else is all math. So this is the experimental science. Once you verify this happens in reality, then math dictates the rest of this. So hopefully you enjoyed this little series of lectures, and yeah, hopefully it amused you if nothing else.